noticed the smell. Her husband had been diagnosed with Parkinson's. She was part of a support group and got real brave. And so then they gave her 12 t-shirts, and half of them were worn by people with Parkinson's so that the smell was there. Half of them were not. Can you guys hear me? Okay. Half of them were not. And so they asked her to smell the shirts and to say, yes, they have Parkinson's, or no, they don't. And in the study, out of the 12 shirts, she was correct on 11 of them. That's pretty good. That's actually really good. So there's a couple of things. First off, we have a dot plot that is very symmetrical. So 1, 2, 5 people got exactly 6 correct. One person got 4, one person got 5, one person got 7, and one person got 8. And if you look in the box below that, a couple of you did it twice, and that's great. I do appreciate that. The mean, as we can see, was 6. That was the standard deviation of 1.18. Minimum was 4. Q1 is 5.5. The median is 6. Q3 is 6.5, and the max is 8. Now, with the max being 8, that meant the person that got 8 correct also got 4 incorrect. What I would like to do is I'm going to have it simulate several more times. Let me just do 10 and add the data. So it's just going to run a simulation, and it should add the data to our plot here. So now we're looking at 19. Notice that 6 is still way up there. And it was a simulation. Okay. Max is 9, so now someone's only missed 3. Now, like I said, this is just a simulation. Have you guys ever heard of the law of large numbers? Okay. So if you flip a coin, you either have heads or tails, right? So if you flip it one time, you're going to get one of the two. Theoretically, if you flip that coin twice, one time you'll get heads and one time you'll get tails. Y'all agree? Theoretically, that's what should happen. If you flip that coin 10 times, theoretically, 5 of those times would be heads and 5 of those times would be tails. Does that really happen? Most of the time, no. You can flip a coin 10, 15, 20 times, and they can all be heads, or they could all be tails, or 15 and 5. But what happens is the more you do something, the more you flip that coin, if you keep track of how many heads and how many tails, the closer you get to that theoretical probability of 50%, which is what we expect because a coin has 2 choices. So the more that we do this Parkinson's disease thing, the more we're going to have, with that 6 being right there in the middle, believe it or not. So now I want to share with you the video, the results.
She got them all right, apart from one. That person went on to develop Parkinson's. Scientists believe that Parkinson's may cause a subtle change in the skin's natural oil, and are working to develop a test that could help diagnose the disease even before physical symptoms occur.
This is a significant new area to research into. There are many scientists looking to do early diagnostics. We all want to do that. We want to be able to tell people, unfortunately, but tell them that they've got a disease earlier than is currently happening. We can find that molecular signature, find a test for it at an early stage. That's when the breakthrough will be. So this is the beginning of the breakthrough.
Joy's husband Les died earlier this year, but the hope is that through science and research, the phenomenon that is her sense of smell will help reverse the destructive power of a disease for which, as yet, there is no cure. Mike McCarthy, Sky News, Manchester.
Okay, so as you saw there, she was 11 for 12, but actually she was 12 for 12. One person that wore a shirt had never been diagnosed with Parkinson's, and then later on was diagnosed with Parkinson's. So statistics and experimentation are used so much in the medical field. All right, so we're going to start out with one variable stuff, and we're going to talk about a lot of definitions. Statistics, when you first start out, there's a lot of definitions and words. Most of the time they mean what you think they should mean, but occasionally they might mean something just a little bit different. So we're just going to kind of go through some definitions, and we're going to do some examples. But first off, what is statistics? Statistics is about analyzing. Now, I feel confident in saying that you guys have probably contributed to giving data to something. You've taken surveys, you may have even conducted surveys. I'm pretty sure when you were in about kindergarten or first grade, you ran around and you asked everybody, what's your favorite color? And then you put them on a little bar graph in kindergarten, or you asked them what their favorite ice cream flavor was. You were gathering data way back then. And we use data for lots and lots of things. The United States has a thing called a census, and we'll talk more about census later, but the census happens every 10 years, and it's where they gather data about everybody that lives in the United States and the territories that the United States owns. Everybody's data, ages, occupations, and things like that. And we have people in our government that use that data to determine when and where they need to build new roads and schools and hospitals and things like that. So statistics plays an important part in just about every profession. I can't think of a single one that doesn't require you to take a statistics class of some sort. Some have you take more than one, but most have you take at least one statistics course. And so this is your statistics course, and you guys will do fabulous on the AP exam. I am a reader for the AP exam. In other words, I grade them every year. I spent 2 weeks in Tampa, Florida, grading AP statistics exams. And so I kind of know what we're looking for. And I'm going to guide you guys on being very meticulous, but we also, at the same time, you don't want to say too much, because when we're scoring those papers and a kid says, you know, you can generalize this to the population because they were randomly selected, and if you stop there, you get credit. But then if you say and randomly assigned, then you don't get credit. So we have to create that balance. And so we need to know what these words mean so that when we use them in a correct manner. Okay? And the information is organized using what we call variables. And that line did not print on my paper for some reason. So we'll use the word variable a lot. And yes, variable is like an X, but a variable is a value. Okay, so we're going to get to that definition here in just a second. So individuals are objects that are described by a set of data. Now they can be described numerically. They can be described characteristically, like brown eyes, blue eyes, male, female, tall, short. I mean, you would have to have a definition of tall and short, but so they're described by some kind of set of data, whether it's numerical or not. Individuals can be people, they can be animals, they can be objects. There's a lot of cars manufactured around the world, and there are lots and lots of data about cars. So that would be an object. But when you're analyzing the data, those cars are known as individuals, which is kind of different, right? Variables are characteristics of individuals. Choose one of my classes. So last semester I had a class that had 28 students, and in that class, 7 of those students wore glasses. So wearing glasses would be the variable that we were looking at, that we were studying of those individuals. Okay. We do have different kinds of variables. They are categorical and they are quantitative. Categorical can also be called qualitative. Place individuals into specific groups. Those who wear glasses would be a group. Those who don't wear glasses would be a group. Those who have blue eyes would be a group. And those who have brown eyes would be a group. Those who have green eyes would be a group. So you're not limited to just 2 groups either. And those are the values that you can do arithmetic with. You can add, you can subtract, you can multiply, you can divide. You can do some kind of arithmetic operation with those variables. Now we do have quantitative variables are categorized into 2 different categories. One is called discrete. Okay, so discrete variables are those that you can count. Like pick it up, 1, 2, 3, 4. So discrete are countable. And usually you will think of those like the number of something. That would be a discrete variable. The other quantitative variable is a continuous. So discrete variables are countable. Continuous variables, we usually think of those as measurable. So we're going to note some examples of categorical variables and of quantitative, both discrete and continuous. So categorical, we've already talked about eye color, gender, color of eyes, handedness. In other words, left-handed or right-handed. That is a characteristic, right? Favorite color. Okay, so those are categorical variables, specific groups. Quantitative variables, discrete examples would be the number of birthdays. In y'all's case, it would be the number of AP classes you're taking. It can be the number of people in a room, on a bus, in a plane, in a stadium, okay? Those are discrete. They are countable. Those would be numbers, okay? Continuous, they're still numbers, but continuous would be things like weight. If you ask somebody what they say and they say, I weigh 120 pounds, do they weigh 120 pounds exactly? No. They might weigh 120.1 or 120.1397, right? Somebody's height. Okay, so when you are looking at height. You read a statistic on the back of a baseball card, it says that the player is 6'4". Are they really exactly 6'4"? Most likely not. Age is also continuous. Emma, how old are you?
15.
15? Are you exactly 15? Like right this minute you turned 15?
No.
No. So only one time could you say you're 15 and you really be 15. Because you could be 15 years and 3 hours old, right? On your birthday. Okay. So age is continuous. Generally, when we're thinking about continuous, if it can be written as, or if it has a decimal involved, it is usually a continuous thing. All right, you do need to be careful though, because just because something is a number does not mean it is a quantitative value. Anybody think of a number that is categorical? Some kind of number that describes a characteristic of you.
Postal code?
Say it again.
A postal code or a zip
Postal
code?
code, yes. In the United States, we call them zip codes, but postal code. Okay. Now, postal codes have a meaning. The first three numbers start out like all the places in your area should have the first three numbers and then the others change. But postal codes are categorical. Those numbers have no meaning mathematically. All right, so discrete variables, those are the ones where counting makes sense. And then on the notes I've got, decimals would not be an appropriate way to record discrete data. You're going to see a lot of discrete in some sections of this course where we talk about the number of successes, the number of failures, the number of trials. Okay, so those are some, we're going to be doing quite a bit with discrete variables. Excuse me. And in continuous variables, they are numerical values where decimals are appropriate. And it usually involves some form of measuring. So a long time ago when I was in one of my early statistics courses, I don't even remember if it was a statistics course, the professor was talking about discrete and continuous, and he gave us an example of cereal and milk. And he said, think of that bowl of cereal, Cheerios, Lucky Charms, whatever it is you eat, as having both discrete and continuous variables. The cereal is the discrete variable. You can pick up that cereal and count it one by one. But the milk, if you dip your spoon in the milk and eat that milk and then dip the spoon in the milk again, you don't get the same amount of milk every time. Even if it's the same spoon, there's going to be a little bit difference in the amount of milk in that spoon. So the discrete would be the cereal, and the continuous would be the milk. And that's just one little way that might help keep that straight. All right, there's two notes that we have on here. The difference between them isn't always clear. Usually when you're talking discrete, you will see the words number of. Age, we've already talked about. Age is a continuous variable to most everybody I know in the math world and statistics world. Even though, you know, when I asked her how old she was, Emma said she was 15. Just because she answered 15 doesn't mean she's exactly 15. Now, in examples that we are going to talk about it as like it's a discrete variable, but I will remind you of that when we do those examples. All right, so let's look at some tables and some data. Is this the second page of your notes? Okay. Excuse me. I am so sorry, guys. I have allergies that would just, yeah. All right, so you're going to see a lot of data, and the easiest way for us to display that data is when we use a table. And you guys have used tables for years for different kinds of things. So this table lists the first 10 United States presidents, the political party of whom they were with when they were elected, and the state that in which they were born. So we have George Washington, who was a Federalist. We don't even have that party anymore, and he was born in Virginia. John Adams was a Federalist, born in Massachusetts. Thomas Jefferson, and we had a party called the Democratic Republican. Now we have one of each. He was born in Virginia, along with James Madison, and James Monroe. John Quincy Adams, the son of John Adams, was a Democratic Republican born in Massachusetts. Andrew Jackson was a Democrat from South Carolina. Martin Van Buren, a Democrat from New York. William Harrison, a Whig from Virginia. And John Tyler was also a Whig from Virginia. We don't have any of those parties in it. Well, we still have Democrats, but I don't even think it's the same values anymore. So this data is right there. It's in a table. We can make sense of this table. But what we want to do is we want to use this data to make some kind of decisions. So we have the president. He's our first column. His party is our second column, and his state of birth. Now, I did not label the columns when I typed up the notes because I wanted to make sure that you saw me actually label those columns. Labeling is super important. If I had not had the words up here, if I just had this list of these guys' names and these names and these states, you could have come up with all kinds of things. You may or may not have known who they were. Okay, so we always want to be very strict with our labels. Make sure that anybody reading anything we do can follow along. All right, so what we want to start with is called a one-way table. And we're going to count the number of Federalist. We're going to count the number of Democratic Republican, count the number of Democrats, and the number from the Whig Party. Now, I've told you at the top that there are 10 presidents, so our count should add up to 10. Okay, so how many of the first 10 United States presidents were Federalist?
2.
2 of them. So our count would be 2. Now, you can count them and put the alphanumeric number, or you can use what's called tally marks or hash marks. Okay, so the tally mark way would be 2 little lines. That does not say 11. And we'll see it here in just a minute when I do more. All right, how many of the Democratic Republicans were president for the United States?
4.
4 of them. So you can use the Arabic number or you can use the tally marks. How many of them were Democrat?
2.
2 Democrat. And we'll put both representations. And how many Whigs?
2.
2 as well. All right. Easy enough, right? We know that there's 10 of them. And if you add 2 plus 4 plus 2 plus 2, you also get 10. Okay, so that was pretty easy things. Now, the relative count, that's where you get in the out of. So in the Federalist Party, 2 out of 10. So that would be our fraction, 2 out of 10. The Democratic Republican, 4 out of 10 is our relative count. The Democrat, 2 out of 10. And the Whig is also 2 out of 10. All right, so we can have the count. We can also refer to counts as frequencies. Frequency is how many times does something happen. Is Tim Hortons still a thing? Okay, so you go to Tim Hortons twice a week. Okay, that's how many times you frequent Tim Hortons, right? All right, so how many of the first 10 United States presidents were born in Virginia?
6.
6 of them, good. Okay, how about New York?
1.
South Carolina?
Also 1.
And Massachusetts?
2.
2. So these numbers better add up to the number of presidents that we have up here. If it doesn't, we've missed something, right? So if we add 6 plus 1 plus 1 plus 2, that gives us our 10. And we refer to the 10, the total, as N. Okay, so N is the number in our sample. Lowercase n is the number in our sample. So the relative frequency, guess what? It looks just like the relative count. So the relative frequency for those born in Virginia is 6 out of 10. New York is 1 out of 10. South Carolina is 1 out of 10. And Massachusetts is 2 out of 10. So our fractions, if we add 6 over 10 plus 1 over 10 plus 1 over 10 plus 2 over 10, what do you get? It's not a trick question, I promise.
You just get 1.
You get 1, okay? And that's the cool thing about statistics and probabilities. Probabilities, the 1 stands for 100%. So if you wrote 100% as a decimal, it would be 1.00, right? So this, if you add them all together, you get 100% of our data. So this fraction adds up to 1. So now when you think about it, the most you can have of anything is 100%. You agree? And the least you can of anything you can have is 0%. So in statistics, a lot of the numbers we deal with, the probabilities in particular, are all between 0 and 1. So we're only using a little bit of that number line that you've learned about all your life, right? Statistics is more logical thinking and reasoning. And sometimes you have to think backwards. So, of our list of the first 10 presidents of the United States, how many were not Democrat?
8.
8. Because if they weren't Democrat, they were all the others, right? So that's kind of how you have to get your brain to working. Now, we won't do a lot with one-way tables. Generally in statistics, we like two-way tables. Two-way tables give us a little bit more information, and in just a small of an area. So this is our two-way table. And so we're going to do some tallies just to kind of get things going. So we're looking at the parties, and the parties are Federalist, Democratic, Republican, Democrat, and Whig. And we're also looking at the state that they were born in: Virginia, North Carolina, South Carolina, and Massachusetts. All right. So looking at our data, we had at the top, there were 2 total that were Federalist, right? In that one-way table. How many of those Federalists were born in Virginia?
1.
1. How about New York?
0.
0. How about South Carolina?
0.
0. And because I know that 2 of those presidents were Federalists based on our one-way table, I hope there's 1 born in Massachusetts. Is that true? Yes. All right, so the Federalist column has to add up to 2. Ours does. 1 plus 0 plus 0 plus 1. Now, this is where the tally marks might come in handy if you wanted to look at the data up here and mark them as you go. You know, Federalist Virginia, Federalist Massachusetts, and do it that way. Either way, or you can just count them because this is a rather small data set. So, how many of our Democratic Republicans were born in Virginia?
3.
3 of them. Now, looking at our one-way table right above, we only had 4 Democratic Republicans. So either we're going to have a 1 for New York or South Carolina or for Massachusetts. Where's that 1 going to go?
Massachusetts.
It's going to go in Massachusetts because John Adams was, no, not John Adams, sorry. John Quincy Adams was a Democratic Republican from Massachusetts. All right, so then the Democrat column. I can see above that we have 2. How many were born in Virginia?
0.
0. How about New York?
1.
Okay. How about South Carolina?
0.
No, there was 1 Democrat in South Carolina. Andrew Jackson. Well, since I've got my 2 here, there were no Democrats from Massachusetts. There was a Democratic Republican and there was a Federalist. All right, so you guys fill in the Whig column and then tell me where I need to put numbers. All right, so if we start at the top of the column, what number goes in this top box?
2.
2. How about the second box?
0.
Okay. Third box?
0.
And the fourth one?
Also 0.
Also 0. There were 2 wigs in the list. So now if we add these across, 1 plus 3 plus 0 plus 2, that gives us 6. So there were 6 total from Virginia. 1 was a Federalist. 3 were Democratic Republicans. There were no Democrat, and 2 were Whigs. So see how a lot of information on this table. So New York had 1. South Carolina was 1. Massachusetts, 2 of the presidents were from Massachusetts, the Adams boys. And if we have done it correctly, our total here will be 10, and our total across is also 10. So when you have total columns for each, if you have a total column for each of the rows and a total row for each of the columns, they have to add up to the same thing. Okay, those must be the same numbers. If they're not, you have a mistake somewhere. All right, so these are not always, this is a good way to show some types of data. We have other ways, and we make graphs. You guys have done pie charts, and you have done dot plots. You saw a dot plot earlier. And when we do graphs, we want to be able to visualize them, and that gives us a better idea of the distribution. Think about the word distribution. Give out, right? If you play cards, you distribute the cards. You distribute to each player. Are any of you guys from big families, like lots of children? No? I am one of 6 children, and when I was growing up, my mother would make a plate of sandwiches and she would distribute them. Each of us would get one, right? Well, distribution tells us what values the variable takes and how often it takes it. So all of the variables are represented in that distribution. All right, so one way that we represent data is in a bar graph. And I've given you some parameters about a bar graph. So we're going to create a bar graph. And we're going to use the presidents that we have. So when you're creating any graph, label, 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 label. I can't stress it enough. Too often, people will make a graph and you won't know what they're talking about. You have to label. You have to make it so that it's very clear what you are doing. Now, in this one, we're going to have the x-axis contain the categorical variable. In other words, the political party. And the y is going to display the count, or you can do percentages. Each of the categories is going to have its own bar. So it's going to have that vertical bar. Those bars cannot touch. Okay, for a bar graph, the bars do not touch. And we can do it in whatever order we want to do it. We can do it alphabetically. We can do it from where the first one talks about being a Federalist, and then Democratic Republican, and then Democrat, and then Whig. It doesn't matter. So we're going to create this bar graph. So first off, we need some axes. And guys, I do a lot of freehand drawing, and sometimes my lines are straight and sometimes they're not. I will go ahead and ask for forgiveness. All right, so here's my axes. And my frequency is going to be the y-axis. And so I need numbers. What was the most number that we had in a political party? There were
Federalist.
the Democratic Republicans had 4. That was the most, right? So we need to go up to at least 4. And I kind of like to go up a little higher. So I'm going to turn my paper just to make writing easier. So if this is 4, 5, 3, 2, 1. All right, so I did my little marks so I could follow along. So 1, 2, 3, 4, and 5. So if you didn't know that we were doing a bar graph about the political parties of the first 10 United States presidents, you would know that we're doing that we're creating a graph that the highest value on it's going to be 5 or less, because that's as far as I numbered it. All right, so if we do it in the same order that we've had everything else, first off, we want the Federalist Party. And there were 2 of those. So we create a bar that is too high. Remember doing these in kindergarten with your favorite colors? Yeah. Even in Canada, they do the kindergarten the same way. Everywhere they do it. All right. The second one was the Democratic Republican in our list. Yes. I'm going to abbreviate Dem/REP. And of those, we had 4, so my bar is going to be 4 high. The third category was Democrat. And there were 2 of those. So my bar is going to be 2 high. And then our final political party is the Whig Party. And there were 2 of those. So my bar will be 2 high on that as well. So now, just looking at the graph, if I didn't know the numbers and I'm looking at the graph, I'm going, okay, there was more of this column than the others, right? There's one thing that we have to do left, and that is we have to give our graph a title. And in the real world and in a good way, the title of this graph would be Political Parties of the first 10 U.S. presidents. Now, if you notice, I pretty much parroted what they had right here. And actually, I did parrot. Exact same thing, okay? But notice the specificity. I was very specific in labeling my graph. You know there should be 10 total. So if you add 2 plus the 4 plus the 2 plus the 2, you're going to get 10. You know what this graph is about. even though, you know, for the last 15 minutes we've been talking about United States presidents, you still can look at the graph and tell all kinds of information. All right, so some of the questions that we can answer from our graph. Of the first 10, which political party was the most affiliated with? I think you guys have been great. You've been very responsive in answering questions, and I appreciate the fact that you don't hide your faces and that I can actually see you, because that always helps when you can see who you're talking to. Do you have any questions for me before we close out this Zoom meeting? Is everybody good? Thumbs up from everybody?